All right, here we are talking about double displacement reactions. There we go. I guess this was our fifth type. The error was on our single displacements last time. This is our fifth type of reaction. So we had combustion, synthesis or combination reactions. Then we had decomposition, then single displacement, and then this will be double displacement. Okay. Um, These are going to be very similar to your single displacement, but in this case, instead of one thing displacing something from a compound, it's going to be two things displacing something from a compound. Now, these ones, like all the other ones, there's something to look forward for in deciding what type of reaction it is. And what you'll be looking for here is that there'll be two ionic compounds as reactants. Okay, so it's always going to involve two ionic compounds as your reactants. Okay? Now, the important thing about these two ionic compounds is because ionic compounds, like we talked about their properties, are generally solids. They don't really become reactive until they are aqueous, which means that they're placed in solution. So in order to do these reactions, you have to dissolve your ionic compounds in water, and then you have to mix those two solutions together. And that's what you would do. So this one is going to actually be two solutions that you pour, or you could place into one into the other. We'll do a version of this a little bit later when we get to perhaps neutralization, which is a subset of a double displacement reaction. All right, products here are also two compounds, usually in the form of some sort of precipitate. There can be a gas formed, or there's water. Now, what we're going to be mostly focused on in this course is looking for a precipitate. We will also mention how gases can be formed from this, and also water. But we'll be mostly looking for the presence of a solid, which is a precipitate. Okay. Now, like we saw with our single displacement, it was the metals displacing other metals. So a lone elemental metal displacing a metal from a compound. And that'd be the same thing here. It'd be metals displacing. And we also saw in the single displacement that two halogens, nonmetals, so a lone elemental halogen would displace a halogen from a compound. And that'll be the true here as well, where two metals will be displacing them from different compounds. Okay? Now we'll treat the idea that the positive ions here will be exchanged in the compound, and also that the negative ions can be exchanged in the compound. Now, on our day one of reactions, we saw a general equation look like this without their charges. This is kind of an expanded form of that, where this is compound one, this is compound two. Okay, so this is a compound. And each compound has a positive ion and a negative ion. Negative, positive ion, negative ion. And then it doesn't really matter how you view it, whether it's the metals that are exchanging or the non-metals. And this arrow is indicating the metals change, but it could be the negative ions also exchanging. But we just view it like this. So the positive ion displaces the positive ion from here. Now, in the single displacement reactions, you looked at the metal activity series to do that. We're not going to use that here. That is only for the single displacement reactions. We're going to use something else. Okay? So this is just a reminder that this is generally what's going to be happening here. Positive ions exchange. So if this is my positive ion here, it's now going to be with a negative ion over here. So A and D will come together, and you have A and D. And then C will come together with B, and you get CB. It's always a plus and a minus. A positive ion with a negative ion. And that's it. So if you looked at in the example down below, we have lead 2 nitrate reacting with Chi, which is potassium iodide. Okay? So if we break this down into the ions, it's going to be Pb 2 plus, you have ONO 3 1 minus, you have K plus, and you have I minus. And it doesn't really matter which ones you picture switching. Let's just go ahead and just take the positive ones, and these will switch places and form products. So the products in this case will be K will now end up with going with the NO3, and the lead will end up going with the iodine. So we're going to get potassium with the nitrate, We'll make sure it's balanced after. I'm going to leave the state for the time being. We'll fill that in after because that's going to be a pretty important thing for us to do. Okay. And then the iodine is going to end up with the lead. That should just be a regular P, not a fancy P. So PbI2, and then we're going to use a bracket here. Okay. Now, of course, I know the formulas from these because I'm just looking at their charge and charge. Oh, looks like I have a charge on this. One is incorrect. This is just a negative. Okay. So these are equal in their charges. So I know that a 1-to-1 ratio. These ones are 2-to-1. This is a smaller charge than this one. I'll need 2 of those to balance that. So I know that I need 2 of those. Let's just double check that it's balanced. We got 1p, 1p. Looks like I already did some previous balancing here. So 2 to put the 2 over here. And looks like we're going to need a 2 here because there's 2 Ks. We need 2 Ks, and then there's 2 NO3s, 2 NO3s. Okay, now what we're going to be looking for here in order to do this is in order for there to be a reaction that actually takes place is we have to see what these charges are or what these states are. So for a reaction to actually involve, there must be a solid formed as we talked about before. So in order for there to actually be a reaction from a double displacement, to categorize it and to say that it's a double reaction, or to say that there is a reaction, is there has to be a solid, a gas, or water formed. Now going back just one little step, and we'll maybe expand on this as part of our AP stuff, but for the most part, what happens to these things when they're placed in solution, these compounds? So if I was to take a sample of PbNO3 2, and I was to pour it into water, what would happen to this PbNO3, this compound, is it would separate into its ions. And it would be an aqueous solution. So when something's aqueous, it means the ion is in there, the compound, but it separates into its ions. So this is now separate from there. And that is true for the Ki as well. So if you put the Ki in there as well, it would separate into the K plus, the I minus, and there'd be a whole whack of them, right? They're whatever you put in there, they'd be separated into their ions. They don't stay together as a unit. Okay. However, when I mix these two things together, so this is where I was trying to get the reaction. I'm going to pour the one into the other to try to get a reaction going. And what should happen is, in order for there to be a reaction, the ions need to come together to form a solid, a precipitate. So that means they have to stay together. If they end up just being separated still, it's just basically you took one solution and you just pour them together, and now everything's mixed up together, but nothing has joined. These are all aqueous at that point. And if that's the case, if nothing forms a solid liquid, solid water or gas, then there's no reaction. So and you would just have a mixture of all these different ions and not an actual reaction that takes place. In order for a reaction to take place in a double displacement, there has to be a solid. So that means that if I mix those two things together, so this is no reaction, okay, and a reaction is going to be looking to see whether there's a solid. Now, the way that we do that is we use this solubility table. Now, this is not a universal solubility table. This is a table that is a simplification of solubility rules. Now, as you move on into chemistry, your chemistry teachers might teach you about the independent solubility rules. This table just organizes those rules into a kind of a tool that you can use to make your life easier without remembering all the solubility rules. However, I will have to add one additional thing on here, is that anything with an H ions or compounds are soluble. Okay, so anything with an H plus or an H is going to be soluble for all intents and purposes in this course. Now, the way this rule works is you go down, the positive ions are at the top, and all the negative ions are down the side. So you look at which positive ion you have and which negative ion you have, and you go just down and across and see what the symbol is. Okay? S's mean soluble, so they remain aqueous. I means they're insoluble, which means that they would be a solid. Things that are sparingly soluble, we will call them a precipitate as well. Sparingly means a little bit of them will be soluble, but there is going to be a precipitate. So we will include as an S. This is, we can't make a prediction. So you'd have to just, there's not enough information to make a prediction based on this table. You can always Google it and see what the solubility rules say for it. But keep in mind, the rules themselves are a general way to make a prediction. The only way to really do it is to do the actual experiment itself. And there are lots of exceptions. Okay, so the rules for some of them aren't always consistent all the way through a type of positive ion or negative ion and so on. So there are exceptions to the rules, but we'll use this table to make our lives a little bit easier and simpler. Okay, so let's apply this to our situation here. We have two solutions that are mixed together with their ions coming together. We want to see if there's any sort of precipitate that forms, and we're going to use a solubility table to do that. So this is K plus and NO3 minus. So we're going to take a look. So K plus, so we're going to go down and we're going to look for NO3 minus. So these two things come together and we get an S, which means it's soluble. So then we place AQ. Then we're going to look for the PbI2. Right? So then we look for Pb2, which is here. And then we're going to look for the iodine, which is going across here. We come down and it's an I, which means it's insoluble. So that's going to be a solid. And then there, that's great, because now we know that we have a precipitate that forms, which means that it would start to form, to accumulate and come out of solution. So this is your solid. And in this case, it's going to be PbI2. And these things will stay in the solution because they didn't form a solid. They were aqueous. So they're still floating around in their solution. Here, let's look at this one here. We're going to look at KCO3 and HCl. It's the same thing. There's two different solutions, right? So this is my acid that's thrown in solution. It's going to separate into its ions. So 2 plus, 2 minus, H plus, Cl minus. We're going to do the old switching again. And we'll see what we end up with. So H is going to be with the CO3. And then the Ca and the Cl. Oop, Cl2. And we'll just add in our some, oh, sorry, you want to balance here. Sorry, I already have that one up there. I'm just over here, okay? So 2 and 2, 2 Cls, 2 Cls, 1 Ca, 1 Ca, CO3. It looks like it's already balanced with the addition of that 2 there, so that looks good. Okay? Now, then we're going to decide what state are these going to be in. And we're going to go back to our solubility table for that. So anything we said with an H was going to be soluble, so this is automatically AQ. And then Ca and then Cl, you see that it's S, which means it's soluble, so that's also AQ. Now, if they're both AQ, there's no solid, gas, or water being produced, then we know that there's not a reaction. These are just going to be floating around in a solution like this, and they're not going to be forming a solid because none of them have come together with enough strength to do that. So we say here that there is no reaction. And that's what I've highlighted down here for you, is that if there's no product, no precipitation, no gas, no reaction occurs. Okay, so product, precipitate, if nothing precipitates out, there's no reaction. All right, now we're going to talk about the situation later as well, because there's a special case for this, but for now we'll leave it the way that it is. Now, a special subset of a double displacement is a neutralization reaction, except it has a special requirement in that the two reactants are acid and a base. Acid and base reacting together is a neutralization. And the products are always the same. So these are the reactants, and the products are always going to be some sort of salt, which is an ionic compound, and water. So here's HNO3, and this is NaOH. This is our base. We know this to be an acid because there's an H with it. An H with a polyatomic. And this is my base. And over here, this is my salt, which is really just means an ionic compound. And then water. Now, this counts as a reaction because if you look at my products, the salt is just dissolved in the solution, just like we saw in our previous examples, but the water comes out as a liquid. Okay? And we saw that water was formed, and that was one of our criteria, right? Water, solid, or gas. And here's water. So we know that this double displacement was a reaction because we have one of the things in the products that we were looking for, which is water. All right. Now, we won't do a lot of this. This will just be something for us to remember in the future more than anything else. But some double displacements produce gases, and you're not going to be an expert at it at this point, but we'll give you kind of a lead into it because it's going to really have you remember how certain things break down. And we'll use just these two cases to look for in the future. Okay? So a gas is formed when one of the products of the double displacement does a decomposition after the double displacement. Okay? So a gas is formed when one of the products decomposes into water and gas. Okay? So here's our example up here. You have sodium carbonate plus HCl, and you end up with sodium carbonate or chloride, and you get you get carbonic acid here. Now the note here is that this acid, if an acid is produced, kind of our oxoacids, they're unstable and they will break down into kind of the reverse of synthesis, right, of how this is formed. So this breaks down into CO2 and H2O. I don't even know if it really stays in that composition. Which is that when these things exchange, this is unstable the way that they organize, and they break down into these two products. So the full equation for this would be you take the two reactants as before, you have the NaCl, which is fine, but then you don't write H2CO3, you go right directly to CO2 and H2O. And this is, see right here, you have aqueous, but now you have a gas and a liquid, and we know that we know that reaction has taken place. Okay, so you'll have to remember that when you see an acid in the products, it's going to decompose. Okay? That is also true for if a base is formed in the products as well. And you'll just have to memorize this one for the most part, knowing that this will break down into ammonia and water, but essentially it's the same process. Okay? There won't be a lot of these, but there might be one or two that pop out in your practice, and there might be one on the quiz that we do a little bit later. All right, so these are just some practice questions that you can work on at the end. Okay? And I'm just going to complete them here, and then you can self-check your work once you do them yourself, and then you can work on the practice that I have also posted to the website after you finish this. Oh, and all the real work here comes from, I'm not going to worry about balancing here, I'm just going to do the formulas. All the work really comes down to see what the states are. So the states are really important. So we're going to emphasize what the state of matter is going to be in each of these here. Okay. I'm not going to worry about balancing, so I'm just going to really worry about the formula and then the states. And once you get familiar with some of them, you don't even have to check them anymore because you already know. Like we've already talked about this one being aqueous, so we don't have to worry about that one and so on. And again, I think all nitrates, they're soluble as well. And we'll just treat that one as being a liquid. Okay. So really all you have to do at this point is then just decide whether they are solid or not. Okay. So I'm just going to try to squeeze them on here. So Na, which is here, and NO3, Na, and NO3 is soluble, so that's aqueous. All right, then AgCl. Ag is here. And then we use Cl, which is here, is insoluble, so it's a solid. So that's a reaction. Okay. We have AgI, so here's Ag, then I, that's insoluble. And then you have KNO3, and I'm going to go ahead. Anything nitrate is soluble. Okay. O8, FeOH, FeOH, E3, here, hydroxide, soluble, so it's a solid, and NaCl, is soluble. KCO3, Ca, calcium, and CO3, and soluble. And you could get two precipitates sometimes. It all depends on what you put together, and so on. So here's KCl, soluble, AQ, and then NaO3. We said any nitrate would be soluble, and SO4, soluble, and then H2O is liquid, and so on. Okay, and that's it.